Open your refrigerator. Look at it. Really look at it. It is a large white or stainless steel box, roughly 5 to 6 feet tall, about 3 feet wide, with a door that opens from the right or the left, depending on your kitchen layout. Inside, there are shelves, drawers, maybe a light that turns on when you open the door. There is a freezer compartment, either on top or on the bottom, or, if you have a side-by-side model, next to the fresh food section. It hums quietly. You do not think about it. Nobody thinks about it. And that is remarkable because the refrigerator is arguably the most transformative appliance in human history. Not the most exciting, not the most dramatic, the most transformative. It changed what humans eat, when they eat it, where they buy it, how far it travels before it reaches them, and how their kitchens, homes, and cities are organized. Before the refrigerator, human civilization was organized around the problem of food spoilage. After the refrigerator, that problem essentially disappeared from daily life in the developed world. And the reason your refrigerator exists in its current form, the reason it hums instead of roaring, the reason it does not occasionally kill you in your sleep, involves one of the most dangerous engineering challenges of the 20th century: the search for a gas that could make things cold without also making people dead. If you enjoy these deep dives into the hidden engineering behind everyday objects, hit subscribe. We release a new episode every week, and I promise you will never open your fridge door the same way again. Before we can understand the refrigerator, we need to understand what came before it, because the thing that came before it is so strange that most people today cannot believe it was real. It was real. It was called the natural ice trade, and it was one of the most improbable industries in American history. In 1806, a Boston businessman named Frederic Tudor had an idea that his contemporaries considered insane. He wanted to cut blocks of ice from frozen New England ponds in winter, insulate them with sawdust, load them onto ships, and sell them in the Caribbean. His friends called him Ice King as a joke. His first shipment, sent to Martinique in 1806, was a financial disaster. Most of the ice melted before it arrived. Tudor lost thousands of dollars. He was mocked in the newspapers. He was nearly bankrupted. He did not stop. Tudor came from a wealthy Boston family, and he burned through the family fortune pursuing this idea. He was imprisoned for debt. He borrowed from anyone who would lend to him. He wrote obsessively in his journals about the ice business, filling pages with calculations about melting rates, insulation thickness, and shipping schedules. His persistence was not optimism, it was obsession. He believed, correctly, that if he could solve the logistics, the demand would be limitless. Hot climates had no shortage of people who wanted cold things. They simply had no way to get them. Over the next 2 decades, Tudor refined his insulation methods, built ice houses at destination ports, and created demand where none had existed. He did not merely sell ice to places that wanted it. He taught people to want ice. In Havana, he persuaded bartenders to serve chilled drinks. In Calcutta, he convinced British colonial officers that iced beverages were essential for surviving the heat. He gave away ice cream to create a taste for cold desserts in markets that had never experienced them. Tudor understood something that most inventors do not. The hardest part of a new technology is not making it work. It is making people care that it exists. He spent as much effort manufacturing demand as he did manufacturing cold. He sent ice to Havana, to Charleston, to New Orleans, to Calcutta. By the 1840s, the natural ice trade was a major American industry. Thoreau wrote about the ice cutters on Walden Pond, noting with wonder that ice from his pond was being shipped to India. Entire towns in New England were economically dependent on ice harvesting. Special tools were developed for cutting, storing, and transporting ice. Railroads built insulated ice cars. Cities built enormous ice houses that could store thousands of tons of ice through the summer. In 1886, the American ice trade consumed approximately 25 million tons of natural ice per year. Think about that for a moment. 25 million tons of frozen water, cut from ponds and lakes with hand saws and horse-drawn plows, packed in sawdust, loaded onto ships and rail cars, delivered to ice boxes in homes across America and around the world. This was the refrigeration system of the 19th century. It was labor-intensive, weather-dependent, geographically limited, and spectacularly inefficient. A warm winter could devastate the industry. The winter of 1880 to 1881 was unusually mild across the northeastern United States. Ponds that normally froze solid by December remained liquid well into January. Ice companies scrambled. Prices doubled. Newspapers wrote about an ice famine as though frozen water were a crop that had failed, which, in a sense, it was. A polluted pond could sicken thousands of customers. The ice frequently contained bacteria, algae, and other contaminants that were invisible when the ice was frozen but became apparent, sometimes fatally, when it melted into drinking water. Typhoid outbreaks were traced to contaminated ice supplies. Cities began inspecting ice sources in the 1890s, but enforcement was spotty, and the science of water contamination was still poorly understood. The product people relied on to keep their food safe was itself a potential health hazard, and it worked well enough that it delayed the adoption of mechanical refrigeration by decades. The icebox itself deserves a moment of attention because it tells you something important about how technology transitions work. An icebox was simply an insulated wooden cabinet with a compartment for a block of ice on top. Cold air, being denser than warm air, sinks. So the ice on top cooled the food below it by convection. You bought a block of ice from the iceman, who delivered it by horse-drawn wagon, usually 2 or 3 times a week. The iceman was a fixture of American urban life for nearly a century. He knew his route the way a postman knows his. He knew which families wanted 25-pound blocks and which wanted 50. He carried the ice with enormous iron tongs, hoisting blocks that weighed as much as a small child up stairways and into kitchens. Children followed his wagon in the summer, grabbing chips of ice that fell off the blocks. The ice sat in a drip pan that you had to empty regularly, or your kitchen floor got wet. Forgetting to empty the drip pan was a minor domestic catastrophe that every household experienced and every household dreaded. The temperature inside the icebox was inconsistent. It started cold when the ice was fresh and warmed up as the ice melted. You could not set a temperature. You could not freeze anything. The icebox kept food cool, not cold. It extended the life of perishables by a few days, which was enough to transform shopping and cooking patterns, but it was a far cry from modern refrigeration. Now, the idea of mechanical refrigeration, using a machine to move heat rather than relying on natural ice, had been understood in principle since the early 1800s. The basic physics is the same as the air conditioner we discussed in a previous episode. You use the evaporation and condensation of a working fluid to absorb heat from one place and release it in another. Multiple inventors built working refrigeration machines in the mid-1800s. Jacob Perkins, an American living in London, patented a vapor compression refrigeration system in 1835. James Harrison, a Scottish-Australian, built practical refrigeration systems for breweries and meatpacking plants in Australia in the 1850s. Ferdinand Carré, a French engineer, developed an absorption refrigeration system using ammonia and water in 1859. Carl von Linde, a German engineer, built improved ammonia compressor systems in the 1870s that became standard in breweries and cold storage facilities. By 1890, mechanical refrigeration was well established in industry. Breweries, meatpacking plants, cold storage warehouses, and ice-making factories all used machine-made cold. But none of these machines were in homes. And they were not in homes for two reasons. The first was size. Industrial refrigeration systems were enormous. They filled entire rooms. They required dedicated operators. They were not something you put in a kitchen. The second reason was the refrigerant problem. And this is where the story gets dark. Every refrigerant available in the late 19th and early 20th century was either toxic, flammable, corrosive, or some combination of all three. Ammonia was the most common. It is an excellent refrigerant from a thermodynamic standpoint. It boils at -33 degrees Celsius at atmospheric pressure. It has a high latent heat of vaporization, and it is cheap to produce. But it is also a poisonous, choking gas that causes severe respiratory damage at low concentrations and death at moderate ones. Even a small leak in a confined space could make a room uninhabitable in minutes. The human nose can detect ammonia at concentrations as low as 5 parts per million, which is well below the danger threshold, so at least you would know something was wrong. That was not true of every refrigerant. Sulfur dioxide was another popular choice. It smells like rotten eggs at low concentrations and causes chemical burns in the lungs at higher ones. It is also corrosive to metals, which meant that the very pipes carrying it were slowly being eaten away from the inside, making leaks more likely over time. Methyl chloride was used in some systems starting in the 1920s. It is colorless and nearly odorless, which makes it more insidious than ammonia because you cannot smell a leak until you are already being poisoned. It attacks the nervous system. Exposure causes confusion, drowsiness, and loss of coordination before progressing to convulsions and death. In 1929, a methyl chloride leak from a refrigeration system in a Cleveland hospital killed over 100 people. This was not a freak accident. It was the predictable consequence of putting a toxic industrial chemical into a machine and then putting that machine inside a building full of people. The public was terrified, and they were right to be terrified. Early home refrigerators, the few that existed, were essentially small industrial refrigeration units shoehorned into a kitchen cabinet. They leaked. The seals failed. The compressor joints worked loose. When they leaked ammonia, you could smell it instantly, which at least gave you a chance to flee. When they leaked methyl chloride, you might not know until you woke up disoriented or did not wake up at all. Newspapers ran stories about families found unconscious or dead in their homes with no visible cause, until investigators traced the source to a malfunctioning refrigerator in the kitchen. Insurance companies began to question whether home refrigerators were an insurable risk. Some apartment building owners banned them outright, refusing to allow tenants to install a machine that could potentially gas an entire floor. Home refrigeration in the 1920s was a technology that worked but was not safe. And safety is not a feature you can compromise on in a kitchen appliance. Nobody buys a product that might poison their family while they sleep. This is a pattern that appears repeatedly in the history of consumer technology. A product can be useful, affordable, and well-engineered, but if it carries a risk of killing its users, adoption stalls. The automobile had to become safe enough before it replaced the horse. The gas stove had to prove it would not explode before it replaced the wood stove. The electric light had to convince people it would not start fires before it replaced the gas lamp. Each of these transitions required not just better engineering, but a shift in public confidence. And public confidence, once lost, is extraordinarily difficult to regain. The engineering challenge was clear. Either find a non-toxic refrigerant or build a machine so tightly sealed that the toxic refrigerant could never escape. The industry pursued both paths simultaneously, and both paths would eventually converge in the same decade. This is the problem that General Electric set out to solve when they developed the Monitor Top refrigerator introduced in 1927. The Monitor Top is one of the most important consumer products of the 20th century, and almost nobody remembers it. It was called the Monitor Top because the compressor sat on top of the cabinet in a cylindrical housing that resembled the turret of the Civil War ironclad USS Monitor. The compressor was hermetically sealed, meaning the entire mechanism, the motor, the compressor, the refrigerant, was enclosed in a welded steel shell with no external joints, gaskets, or openings. If there were no openings, there could be no leaks. If there were no leaks, the refrigerant could not escape into the kitchen. The hermetic compressor did not eliminate the danger of the refrigerant itself. The Monitor Top still used sulfur dioxide, but it dramatically reduced the probability of a leak. GE's engineering philosophy was essentially, we cannot make the gas safe, so we will make the container perfect. The Monitor Top was also quiet. Previous refrigerators used belt-driven compressors that rattled, clanked, and vibrated. The hermetic compressor hummed. That hum, that low, constant, barely perceptible background noise that you hear when your kitchen is otherwise silent, is the sound of a hermetically sealed compressor running. It has not changed in nearly 100 years. Every refrigerator you have ever owned makes essentially the same sound, because they all use essentially the same type of sealed compressor that GE pioneered in 1927. GE was not the only company trying to put a refrigerator in every kitchen. Frigidaire, which was owned by General Motors, had been selling home refrigerators since 1918. Kelvinator had entered the market in 1914. But these early competitors used open-type compressors with belt drives and external seals, which meant they were noisy, required periodic maintenance, and were vulnerable to refrigerant leaks. The Monitor Top's hermetic design was a genuine leap forward. It was not just better. It was a different category of product. It was the first refrigerator you could buy, install, and then largely ignore for decades. The Monitor Top was expensive. It cost between $270 and $525 depending on the model, at a time when the average American annual income was about $1,500. You were paying a significant fraction of your yearly earnings for a kitchen appliance. To put that in perspective, a new Ford Model A cost about $450. A refrigerator cost roughly the same as a car. But it sold. Many families bought them on installment plans, paying a few dollars a month, which was itself a financial innovation that accelerated adoption. The installment plan was not new, but its application to kitchen appliances was. It transformed the refrigerator from a lump-sum luxury purchase into a manageable monthly expense, and it created an entirely new category of consumer credit. Department stores promoted refrigerators alongside washing machines and radios as the essential trio of modern living. Advertising campaigns targeted women specifically, framing the refrigerator as liberation from the daily drudgery of ice management and the constant anxiety of food spoilage. The ads showed gleaming white kitchens with smiling housewives presenting perfect meals. The refrigerator door open to reveal an abundance of fresh food. The message was not just convenience. It was safety, modernity, and upward mobility, all sealed in white enamel. The color itself was deliberate. White suggested cleanliness, hygiene, and medical-grade purity. It was the color of hospitals, laboratories, and sanitation. In a decade when the public was still traumatized by stories of toxic gas leaks, white was the color of reassurance. GE sold over 1 million monitor tops between 1927 and 1936. The reliability was extraordinary. Some units ran continuously for over 30 years. There are monitor top refrigerators still in operation today, nearly a century after they were manufactured. They are the Nokia phones of kitchen appliances. But the refrigerant problem was not truly solved. It was merely contained. The monitor top's hermetic seal was good, but not perfect. Sulfur dioxide leaks still occurred, especially as units aged and the welded seals degraded. And even if the seal held perfectly for the life of the unit, there was the question of disposal. What happened to the sulfur dioxide when the refrigerator was eventually scrapped? Nobody had thought about that yet. The real solution arrived from the same source that solved the air conditioning refrigerant problem, and the same source that created leaded gasoline, Thomas Migley, Jr. As we discussed in our air conditioner episode, Migley developed chlorofluorocarbons, CFCs, at Frigidaire in 1928. Freon 12 was non-toxic, non-flammable, chemically stable, odorless, and had ideal thermodynamic properties for refrigeration. It was, from a pure engineering standpoint, the perfect refrigerant. When Freon replaced sulfur dioxide and methyl chloride in home refrigerators in the early 1930s, the safety problem vanished overnight. You could now put a refrigeration machine in a home and be essentially certain it would not poison the occupants. This was the inflection point. Not the invention of mechanical refrigeration. Not the hermetic compressor. Freon. Freon is what made the home refrigerator safe enough for mass adoption. Sales exploded. In 1930, about 8% of American homes had a mechanical refrigerator. By 1940, it was 44%. By 1950, it was over 80%. By 1960, it was in virtually every American home. The adoption curve is striking because it happened during and despite the Great Depression. The 1930s were the worst economic decade in American history, yet refrigerator sales grew every single year. People who could barely afford food were buying machines to keep food cold. This tells you something about how fundamental the refrigerator was perceived to be. It was not a luxury. It was infrastructure. It was the difference between food that lasted and food that did not, between safe milk for your children and milk that might make them sick. The refrigerator went from luxury to necessity faster than almost any major appliance in history. And its consequences rippled outward in ways that nobody anticipated. The first and most obvious consequence was the death of the iceman. The natural ice industry, which had employed tens of thousands of workers and sustained entire regional economies, collapsed within a single generation. Ice delivery routes disappeared. Ice houses closed. The tools of ice harvesting, the horse-drawn ice plows, the hand saws, the ice tongs, went from essential implements to museum curiosities. The ice wagons that had been as common as mail trucks on American streets vanished in less than 20 years. Ice companies tried to adapt. Some of them began manufacturing machine-made ice, shifting from harvesting natural ice to producing artificial ice in factories. But the home refrigerator eliminated the need for delivered ice entirely, and even the factory ice business eventually contracted to serving restaurants, fishmongers, and other commercial customers. The transition was not gentle. Thousands of workers lost their livelihoods. Entire communities that depended on ice harvesting were economically devastated. The ice cutters of Maine, who had harvested the Kennebec River for generations, found themselves with skills that nobody needed and equipment that nobody wanted. This is one of those historical transitions that we tend to romanticize in retrospect, but that caused real suffering at the time. The Iceman did not simply walk off stage. He was pushed. There is a phrase in economics called creative destruction, coined by Joseph Schumpeter. It describes the process by which new technologies destroy old industries while creating new ones. The refrigerator is a textbook example. The ice trade employed cutters, haulers, deliverymen, ice house operators, and tool manufacturers. The refrigerator industry employed factory workers, electrical engineers, compressor designers, refrigerant chemists, appliance salesmen, and repair technicians. The total employment may have been similar, but the specific people who lost their jobs in the ice trade were not, in most cases, the same people who gained jobs in the refrigerator industry. Technological transitions redistribute prosperity. They do not create it evenly. The second consequence was the transformation of the American diet. Before refrigeration, the American diet was heavily constrained by what was locally available, in season, and could be preserved through smoking, salting, pickling, canning, or drying. Fresh meat was consumed within a day or two of slaughter, which meant you either lived near a butcher or you did not eat fresh meat. Fresh milk was consumed within hours of milking, unless you had ice to keep it cool. Fruits and vegetables were seasonal. You ate apples in fall, strawberries in summer, and root vegetables in winter, because those were the things that were available. The American diet before refrigeration was regional, seasonal, monotonous, and frequently unsafe. Foodborne illness was endemic. Spoiled food was not an occasional inconvenience. It was a constant threat. The refrigerator changed all of this. You could now buy fresh meat on Monday and eat it on Thursday. You could keep milk for days without it souring. You could store leftovers. You could buy in bulk. The entire rhythm of food shopping shifted from daily trips to the market to weekly trips to the grocery store. And this shift, in turn, enabled the grocery store itself. The modern supermarket is architecturally and economically impossible without refrigeration. The cold chain, the unbroken sequence of refrigerated transport, storage, and display that moves food from farm to fork, is the invisible infrastructure that makes the modern food system work. A head of lettuce grown in California can be harvested, cooled to near freezing within hours, loaded into a refrigerated truck, transported 3,000 miles across the country, stored in a refrigerated warehouse, placed in a refrigerated display case at a supermarket in New York, purchased, brought home, and stored in a home refrigerator, all while maintaining a temperature between 32 and 40 degrees Fahrenheit. At no point in this journey does the lettuce leave the cold chain. If any link in the chain breaks, the lettuce spoils. The entire system works because every component, from the farm cooler to your crisper drawer, uses the same basic technology, the vapor compression refrigeration cycle. The cold chain did not emerge all at once. It was built link by link over decades. Gustavus Swift, the Chicago meat packer, pioneered refrigerated rail cars in the 1880s, allowing him to slaughter cattle in Chicago and ship dressed beef to markets on the East Coast. Before Swift, live cattle were shipped by rail from the West to eastern slaughterhouses, a process that was expensive, stressful for the animals, and resulted in significant weight loss during transit. Cattle lost weight during the journey, and a significant percentage died in transit, which meant the railroads were hauling bones, hooves, hides, and offal 3,000 miles only to discard them at the destination. Swift realized that if he slaughtered and dressed the cattle in Chicago, he could ship only the edible portions, saving 60% on shipping costs per pound of beef. But the Eastern railroads resisted him. They had invested heavily in livestock cars and did not want to see that business disappear. Swift had to build his own fleet of refrigerated cars and negotiate deals with smaller railroad lines that were willing to carry them. He fought the established railroads, the local butchers who feared his competition, and the consumer skepticism about meat that had been killed hundreds of miles away. He won on all fronts. His refrigerated cars transformed Chicago into the meatpacking capital of the world. The Union stockyards, which processed millions of animals per year, existed because of refrigeration. Upton Sinclair's The Jungle, the novel that exposed the horrors of the meatpacking industry and led to the Pure Food and Drug Act of 1906, was set in those yards. Refrigeration made the industrial meatpacking system possible. Whether that system was a good thing depends on your perspective, but its existence was a direct consequence of the cold chain. The cold chain also made global food trade possible. Before mechanical refrigeration, international trade in perishable food was essentially non-existent. You could ship grain, spices, and preserved foods across oceans, but fresh meat, dairy, fruits, and vegetables were consumed locally or not at all. The development of refrigerated shipping in the late 19th century changed this completely. In 1882, the sailing ship Dunedin carried the first commercially successful shipment of frozen meat from New Zealand to England. The voyage took 98 days. The meat arrived frozen and edible. This single voyage launched a global industry. New Zealand and Australia became major meat exporters. Argentina shipped beef to Europe. Central American countries shipped bananas to North America, creating the banana republics and the United Fruit Company, and a century of political entanglement that continues to this day. The banana you eat for breakfast exists in your kitchen because of refrigerated shipping. So does the New Zealand lamb, the Chilean wine, the Norwegian salmon, and the Thai shrimp. The supermarket itself is a refrigeration machine. If you have ever walked through a large grocery store, you have noticed that the perimeter is lined with open refrigerated cases displaying produce, dairy, meat, and frozen foods. These cases are not sealed. They use a curtain of cold air flowing downward from the top of the case to keep the products cold while allowing customers to reach in and take what they want. This design is called an air curtain, and it is remarkably wasteful. The cold air spills out into the store, which is why the dairy aisle always feels 10 degrees cooler than the cereal aisle. The store's heating system then has to compensate for all the cold air leaking out of the display cases. The energy required to maintain this open-air refrigeration is staggering. A typical supermarket uses 3 to 5 times more energy per square foot than a typical office building, and the majority of that energy goes to refrigeration. Some European supermarkets have begun installing glass doors on their refrigerated cases, which reduces energy consumption dramatically, but which American consumers have been slower to accept, partly because the open case feels more inviting, and partly because Americans are accustomed to reaching in without opening anything. The supermarket is, from an engineering standpoint, a building designed around the cold chain's final link. Every aisle, every display, every checkout lane exists to move refrigerated products from the store's receiving dock to your car and then to your home refrigerator as quickly as possible, minimizing the time any product spends outside the cold chain. The refrigerator also reshaped the physical layout of the kitchen. Before refrigeration, kitchens were organized around the stove, which was the center of food preparation and the primary source of heat for the home in many cases. The kitchen was often the smallest and least prestigious room in the house, tucked away in the back, sometimes in the basement, because cooking generated heat, smoke, and odors that the family wanted separated from the living areas. The arrival of the refrigerator, combined with improvements in ventilation and the transition from wood and coal stoves to gas and electric ranges, gradually transformed the kitchen from a utilitarian workspace into the social center of the home. The kitchen work triangle, the concept that the stove, sink, and refrigerator should be positioned in a triangular arrangement for maximum efficiency, was developed in the 1940s at the University of Illinois as part of a research project on kitchen design. The researchers studied hundreds of homemakers performing routine kitchen tasks and discovered that most cooking activity involved movement between 3 points: where you wash things, where you cook things, and where you store things. The refrigerator was not just added to the kitchen, it reorganized it. Kitchens got bigger to accommodate the new appliance. Counter space increased because you now needed room to prepare the wider variety of foods that refrigeration made available. The kitchen pantry, which had been essential for storing shelf-stable preserved foods, shrank or disappeared entirely as the refrigerator took over the food storage function. Walk-in pantries that had been standard features of Victorian-era homes vanished from floor plans by the 1960s, replaced by cabinets and the refrigerator itself. And the design of the refrigerator itself became standardized in ways that are so familiar we do not notice them. Why is the freezer on top in most traditional models? Because the compressor generates heat, and you want the coldest compartment as far from the heat source as possible. The compressor is at the bottom, so the freezer goes on top. Why are the shelves adjustable? Because the variety of foods people store changed dramatically once refrigeration made fresh produce, dairy, and large cuts of meat available year-round. You need different shelf heights for a gallon of milk, a carton of eggs, and a plate of leftovers covered in aluminum foil. Why does the door have shelves built into it? Because the door is the warmest part of the refrigerator, since it is farthest from the evaporator coil and is exposed to room temperature every time you open it. Door shelves are for condiments, beverages, and other items that tolerate temperature fluctuation. Your eggs, despite what the door shelf might suggest, should technically be stored on an interior shelf where the temperature is more consistent. There is a deeper question here that I think is worth considering. Why does every refrigerator look essentially the same? Why has the basic form, a tall rectangular box with a front opening door, not changed significantly since the 1950s? This question sounds trivial, but it is actually a profound one about industrial design. Other appliances have changed dramatically in form over the same period. Televisions went from bulky cathode ray tubes to flat panels. Telephones went from rotary dial boxes to pocket-sized touchscreens. Computers went from room-sized machines to devices thinner than a magazine. But the refrigerator looks essentially the same as it did in 1955. Part of the answer is that the form follows the physics. A rectangular box maximizes interior volume for a given footprint. A front opening door provides the best access to contents. Vertical orientation takes advantage of cold air's tendency to sink, keeping the coldest air at the bottom and allowing it to stratify naturally. The design is not arbitrary. It is optimized for the thermodynamic reality of how cold air behaves in an enclosed space. But part of the answer is also cultural lock-in. Kitchen cabinets are built to standard dimensions. Counter heights are standardized. The space allocated for a refrigerator in most American kitchens is a specific width and depth. Builders expect refrigerators to fit in a specific opening. Consumers expect refrigerators to look a certain way. The design has become so standardized that deviation from the norm feels wrong. European and Asian refrigerators tend to be smaller and come in a wider variety of form factors, partly because kitchens in those regions are smaller and less standardized. But in America, the full-size refrigerator has become as architecturally fixed as a doorway. It is a piece of furniture that masquerades as an appliance. The environmental story of the refrigerator parallels the air conditioner story, because the same refrigerants are used in both. Freon and other CFCs were the standard refrigerant in home refrigerators from the 1930s through the 1980s. For 50 years, nobody questioned them. They were stable, safe, effective, and apparently harmless. Then, in 1985, Scientists discovered the ozone hole over Antarctica, and the entire chemical family that had made safe refrigeration possible was revealed to be destroying the atmospheric layer that protects life on Earth from ultraviolet radiation. The Montreal Protocol, signed in 1987, mandated the phase-out of CFCs. Refrigerator manufacturers switched to HFCs, hydrofluorocarbons, which do not destroy ozone but are potent greenhouse gases. Some HFCs have a global warming potential over 1,000 times greater than carbon dioxide. The industry had traded one environmental catastrophe for another. More recently, the industry has begun transitioning to hydrocarbon refrigerants, primarily isobutane, designated R600OA. Isobutane has a global warming potential of 3, compared to over 1,000 for some HFCs. It is flammable, but the quantity used in a domestic refrigerator is tiny, typically less than 150 grams, and modern safety engineering has made the fire risk negligible. Most refrigerators sold in Europe today use isobutane. The United States has been slower to adopt it, partly due to more conservative safety regulations and partly due to industry inertia, but the transition is underway. It is worth noting the irony here. The very first refrigerants, before Freon, included hydrocarbons and other flammable substances. The industry spent a century moving from flammable refrigerants to toxic ones to safe but environmentally destructive ones, and is now moving back to flammable ones, having come full circle with better engineering to manage the risk. The frozen food revolution deserves its own moment in this story because it fundamentally changed what the refrigerator was for. In the early 1920s, a young biologist and adventurer named Clarence Birdseye was working as a fur trader in Labrador, Canada. He observed that the Inuit people froze fish almost instantly by leaving them on the ice in the fierce Arctic wind, where temperatures dropped to -40 degrees. When these fish were thawed and cooked weeks later, they tasted remarkably fresh. Birdseye realized that the speed of freezing was the critical variable. Slow freezing, which was what conventional cold storage achieved, formed large ice crystals that punctured cell walls, turning food mushy and tasteless when thawed. Fast freezing formed tiny ice crystals that left cell walls intact. The food's texture and flavor were preserved. Birdseye spent years developing equipment that could flash freeze food at commercial scale. His method used 2 refrigerated metal plates that pressed against the food from both sides, freezing it from the outside in at extremely high speed. The result was food that could be frozen in minutes rather than hours, and the difference in quality was dramatic. He was granted multiple patents in the late 1920s and early 1930s. In 1929, he sold his company and patents to the Postum Company, which became General Foods, for $22 million, an enormous sum at the time. Adjusted for inflation, that is roughly $400 million today, for what was essentially a method of making food very cold, very fast. General Foods launched the Birdseye brand in 1930, selling frozen vegetables, fruits, fish, and meat in retail stores. The products were initially unsuccessful because most stores did not have freezer display cases and most homes did not have adequate freezer compartments. Grocers were skeptical. Consumers were wary. The idea that food could be frozen for weeks and still taste good was counterintuitive to people who associated frozen food with the mushy, tasteless results of slow freezing. But as refrigerator designs evolved to include larger and more capable freezer sections, and as Birdseye's quick freezing method proved its superiority over and over, frozen food adoption grew steadily. The real breakthrough came in 1954, when Swanson introduced the TV dinner. The story goes that Swanson had massively over-ordered turkey for Thanksgiving and had 260 tons of frozen turkey sitting in refrigerated railroad cars with nowhere to go. The turkey was circling the country on rails, essentially homeless, accumulating storage fees. A salesman named Jerry Thomas suggested packaging the surplus turkey with side dishes in a compartmented aluminum tray that could be heated in the oven and eaten in front of the television. The tray design was inspired by airline meal trays, which Thomas had seen on a recent flight. The compartments kept the turkey, the cornbread dressing, the peas, and the sweet potatoes separate, so they could each heat at their own rate. The first TV dinner sold for 98 cents. Swanson sold 10 million of them in the first year. The TV dinner was not great food. It was convenient food. And convenience, as the microwave would later prove again, was the most powerful force in the American food industry. The TV dinner also coincided perfectly with the rise of television itself. Families were eating in the living room for the first time, and they needed food that could be prepared quickly, served without real dishes, and consumed with one hand while the other held the remote. The freezer made this possible. The freezer compartment evolved from a small ice cube making box at the top of the refrigerator to a major food storage facility. Ice cream, which had been a rare luxury requiring a special trip to the soda fountain, became an everyday food. Frozen pizza, frozen burritos, frozen waffles, frozen vegetables, frozen fruit, frozen juice concentrate. An entire parallel food industry grew up around the freezer. Today, the frozen food market in the United States alone is worth roughly $65 billion per year. None of it would exist without the freezer compartment in your refrigerator. There is another dimension of the refrigerator that has nothing to do with food preservation and everything to do with human behavior. The refrigerator is the only appliance in your home that also serves as a bulletin board. Look at the front of your refrigerator. What do you see? Magnets. Children's artwork held up by magnets. Grocery lists, family photographs, school calendars, takeout menus, save-the-date cards, postcards from friends on vacation, dentist appointment reminders. The refrigerator door is the largest flat, vertical, magnetic surface in most kitchens, and humans have instinctively turned it into a communication hub. No other appliance serves this function. Nobody posts family photos on their dishwasher. Nobody sticks the grocery list to the washing machine. The refrigerator became the household bulletin board because of a confluence of physical properties. It is tall, it is flat, its exterior is steel, magnets stick to steel, and it is located in the kitchen, which is the most trafficked room in most homes. This was not designed. It emerged. It is one of those accidental social functions that reveals something about how humans organize domestic space. The modern smart refrigerator takes this bulletin board function to its logical and perhaps absurd conclusion. Samsung, LG, and other manufacturers now sell refrigerators with built-in touchscreens, Wi-Fi connectivity, interior cameras, grocery management apps, recipe suggestions, and the ability to order food online directly from the refrigerator door. You can see what is inside your refrigerator from your phone while you are at the grocery store. You can stream music through your refrigerator's speakers. You can leave video messages for your family on the refrigerator's screen. Whether any of this constitutes genuine utility or is simply feature creep in the tradition of the microwave's unused popcorn button is an open question. The compressor inside these smart refrigerators is, of course, the same hermetically sealed unit that GE pioneered nearly a century ago. The intelligence is all on the door. The cold is unchanged. The global story of refrigerator adoption mirrors what we discussed in the air conditioner episode. In the developed world, refrigerator ownership is near universal. Over 95% of American homes have one. In Europe, Japan, and South Korea, penetration is similarly high. But in much of the developing world, refrigerator ownership is still growing. In India, roughly 30% of households have a refrigerator. In sub-Saharan Africa, it is below 10%. In these regions, the absence of refrigeration has consequences that go far beyond convenience. Without cold storage, farmers in tropical countries lose between 30 and 50% of their harvest to spoilage before it ever reaches a market. Fruit rots in the field. Milk sours within hours of milking. Meat must be consumed the same day it is slaughtered, or it becomes unsafe. The lack of refrigeration is not just a quality of life issue. It is a food security issue, a public health issue, and an economic development issue. As incomes rise in these regions, refrigerator adoption will follow the same explosive curve that the United States experienced between 1930 and 1960. The implications for global energy demand, refrigerant consumption, and food waste patterns are enormous. If every household in India and sub-Saharan Africa that currently lacks a refrigerator were to acquire one, the additional electricity demand alone would require the equivalent of dozens of new power plants. Speaking of energy, the energy efficiency story of the refrigerator is one of the great underappreciated regulatory successes of the late 20th century. In the 1970s, an average American refrigerator consumed roughly 1,800 kilowatt-hours of electricity per year. To put that in context, that is the equivalent of running a 100-watt light bulb continuously for about 2 years. Your refrigerator was the single largest electricity consumer in most American homes, accounting for roughly a quarter of total household electricity use. Today, a typical new refrigerator consumes about 400 kilowatt-hours, while being significantly larger and offering more features. That is a 78% reduction in energy consumption per unit. This improvement did not happen spontaneously. It was driven by federal efficiency standards, first mandated by the U.S. Department of Energy in the 1990s, which set minimum efficiency levels that manufacturers were required to meet. The story behind those standards is worth telling briefly. California led the way in the 1970s, passing the first state-level appliance efficiency standards. Manufacturers initially resisted, arguing that the standards would increase costs and limit consumer choice. But California's market was too large to ignore, and manufacturers found that once they redesigned their products for California, it made no sense to sell less efficient versions elsewhere. Other states followed California's lead, creating a patchwork of state regulations that eventually pushed manufacturers to support a single federal standard for simplicity. Each successive round of standards ratcheted up the requirements. Manufacturers responded with better compressors, improved insulation, more efficient motors, and optimized airflow designs. The result is that even though the total number of refrigerators in the United States has grown substantially, the total energy consumed by refrigerators has actually decreased. This is one of the few examples in consumer technology where energy demand went down while usage went up. There is, however, a paradox built into the refrigerator's success. The refrigerator prevents food spoilage, which should, in theory, reduce food waste. But in practice, the opposite has happened. Americans throw away between 30 and 40% of their food supply. Much of this waste occurs at the household level, and the refrigerator enables it. Because the refrigerator keeps food safe for days or weeks, people buy more than they need. They push older items to the back of the shelf, forget about them, and eventually throw them away when they discover them weeks later in a state of advanced decomposition. The crisper drawer, ironically, is often where vegetables go to die. The refrigerator does not cause food waste, exactly, but it creates the conditions under which food waste becomes easy invisible and habitual. The machine that was invented to solve the food preservation problem has, through its very success, created a new food waste problem. And then there is the disposal question. Approximately 100 million refrigerators are scrapped globally each year. Each one contains refrigerant that must be carefully extracted and either reclaimed or destroyed. Each one contains insulation foam, often blown with now banned CFC or HFC gases, that must be handled as hazardous waste. The foam itself is a significant issue that most people do not think about. The polyurethane foam that insulates modern refrigerators was, for decades, blown with CFC gases. When you crush or shred a refrigerator, the foam releases those trapped gases. A single old refrigerator can contain enough CFC in its foam to equal the greenhouse impact of driving a car for several months. The metals, the glass, the plastics must be separated and recycled. Proper recycling requires specialized facilities that can puncture the sealed refrigerant system, capture the gas, shred the cabinet while containing the foam emissions, and separate the resulting materials into recyclable streams. Improper disposal of old refrigerators releases refrigerant directly into the atmosphere. In many developing countries, where formal recycling infrastructure is limited, old refrigerators are simply abandoned or dumped, their refrigerant leaking slowly into the air. Even in developed countries, compliance is imperfect. The environmental footprint of a refrigerator does not end when it stops humming. It extends decades beyond its useful life, as the chemicals sealed inside it find their way into the atmosphere one way or another. There is one more thing I want you to think about, and it concerns what the refrigerator did to the concept of freshness. Before refrigeration, freshness was a binary condition. Food was either fresh, meaning it had been harvested or slaughtered recently enough to be safe, or it was not fresh, meaning it was spoiled, preserved, or somewhere in the uncertain territory between. You could tell by looking at it, smelling it, and sometimes, regrettably, by tasting it. The refrigerator created a new category: preserved freshness. Food that is technically days or weeks old, but has been maintained at a temperature that slows bacterial growth enough to keep it safe and palatable. The strawberries in your refrigerator are not fresh in the way your great-grandmother would have understood the word. They were picked days ago, possibly a week ago, in a field hundreds or thousands of miles away. They have been cooled, shipped, warehoused, displayed, purchased, and stored, all within a narrow temperature band. They look fresh. They taste reasonably fresh. But they are artifacts of a cold chain, maintained in suspended animation by a continuous application of mechanical cold. The refrigerator did not just preserve food, it redefined what fresh means. There is a remarkable continuity to this story. The basic technology inside your refrigerator, the vapor compression cycle using a hermetically sealed compressor, has not changed in its fundamental principles since the 1920s. The refrigerants have changed. The insulation has improved, from fiberglass to polyurethane foam. The compressors have become more efficient, using variable speed motors and better bearings. Modern inverter compressors can adjust their speed continuously rather than cycling on and off, which reduces energy consumption and eliminates the periodic loud clicking sound that older refrigerators made when the compressor kicked in. The controls have gone digital. Thermostats that were once simple bimetallic strips are now electronic sensors feeding data to microprocessors. But the core mechanism, a fluid that evaporates and absorbs heat inside the box, then gets compressed and condensed to release that heat outside the box, is identical to what GE put in the monitor top in 1927, which is itself identical in principle to what Jacob Perkins patented in 1835. You are keeping your groceries cold using physics that was understood 2 centuries ago, engineered into a practical form a century ago and refined incrementally ever since. In an era when every other consumer technology seems to reinvent itself every decade, the refrigerator's fundamental stability is both reassuring and remarkable. It works. It has always worked. The improvements have been around the edges, not at the core. Next time you hear that quiet hum from your kitchen, consider what it represents. It is the sound of a hermetically sealed compressor, running a refrigerant through a closed loop, absorbing heat from your food and releasing it into your kitchen. It is the sound of a technology that killed the natural ice trade, transformed the American diet, enabled the global cold chain, reshaped kitchen architecture, punched a hole in the ozone layer, and then had to reinvent its own chemistry to survive. It is the sound of 100 years of incremental improvement applied to a single core idea. Move heat from inside the box to outside the box. It is the sound of a machine so successful that we have forgotten what life was like without it. We open the door without thinking. We reach for the milk without gratitude. We close the door and walk away, and the compressor cycles on again, maintaining the cold, keeping the chain unbroken, doing the one thing it was designed to do. Your refrigerator is not just keeping your milk cold, it is the quiet engine of modern civilization. And it hums because GE decided in 1927 that if you seal the compressor tightly enough, nobody has to die.